Okay. One sec. Okay. So last time we were talking about the architecture and so few configurations, right? So let's move on further, right? So this is any query life cycle that we were talking, right? So whenever you execute a query, so then it will be first parsing. So it will validate if there is any syntactical errors or anything, and then it will, so once it is validated, and it will be checking like what is the schema binding. Because if it is uh, person dot person is different, and normal dbo dot person is different, right? So the schema binding, it will validate, right? So whether the schema is bound to the particular, the table is bound to a specific schema, or it is a default schema. DBO is the schema, right? Logical unit. It will validate the schema binding, then it will proceed with further optimization, right? So it will send it to the optimizer. So the query tree, so query tree it will create, and it send to the optimizer. So optimizer is the one which generates a plan. So it will check whether the plan is already exist or not. So how it validates? So there is a hashing, right? So hash value. So in the memory, so it creates a hashing function or algorithm, and based on that, it will search the query and the plan in the plan cache, right? So it will validate the plan is available or not in the plan cache, right? If the plan is not available, so there are different so optimization phases it will follow to get the plan, right? So let's say, for example, if the query is simple, right? So if the query is simple, select star from table, or whatever, like, so simple query, then it will stop any further optimization, and it generates a trivial execution plan, right? So if it is, yeah, so if it is simplification, it generates a say trivial plan. If it is an, so full optimized query, right? So it will go for full optimization, and it checks whether the statistics are updated or indexes are available, or whether the query goes for parallel execution. So all these it will validate and generates a plan, right? So that is what it is. N number of searches it performs internally as quick as possible, right? So it will not keep searching for best plan, right? So it will stop, the for optimization would be stopped when it gets a optimal plan for the execution, right? So the goal of the query optimization is not to find the best execution plan, to find a good enough execution plan, right? So good enough plan is sufficient. So instead of keep searching for the best execution plan, it checks whether the optimal plan is available for the query to execute or not. If it identifies, it will stop then and there, and it generates a plan for the execution, right? So estimated plan. This is the high level, so architecture. So a high level query processing. Now, uh, okay. So one thing to keep in mind, whatever plans in the plan cache, right? So we were talking about the plans stored in the plan cache. So whatever plans stored in the plan cache, all are estimated plans. So everything will be estimated because optimizer generates an estimated plan, and that will be stored in the plan cache, so that whatever plans which are available in the memory, everything is an estimated plan. So until 2019, I would say, like, so until 2019, so we don't cache the actual execution plan, right? Starting from 2019, so there is a method or trace flag that we have to enable starting from 20, sorry, 9, not 2019, 2022 SQL. So starting from 2022 SQL Server, so we have a trace flag to enable to cache the actual execution plan of the query, right? So until 2019, So every plan that we see from the memory is an estimated plan. Even if you enable query store, and from the query store, if you get the execution plan, that is estimated as well, right? So we will talk about the query store later, but for your information, like you will not get actual execution plan anywhere from the memory. So everything, it is an estimated plan, right? So we will talk about the execution plans, query store, whatever it is, and the query performance tuning. But for your information, so whatever plans optimizer generates, that is an estimated plan and stored in the plan cache. And if you get the plan, if you retrieve the plan from the DMVs or from, so query store, whatever traces that you enable, it is a estimated plan, not the actual plan. Okay. Now, so this is good, right? So whatever like queries executing, so where the queries will be executed, so where the queries will be executed and how it is executed. So the query, I mean, whereas like, so where these queries will be run, so who will run the queries? So for example, you are executing this query, let's say. So you're getting output and fine, right? So your SQL server, it is connected to the SQL server and executing, that's fine. So in backend, right, what happened? So every query or every task so that we are executing at the SQL server will be taken care by a thread, will be executed by a thread, right? So thread is nothing but a smallest execution unit of your work, right? So of your task. So thread is nothing but a worker. For example, in a house construction, so you are constructing a house, let's whatever it is. So the house construction, so you need a few people to construct the house. We call them as a worker, right? So each worker will take care of certain tasks and construct the house, build the house, right? The same thing in SQL Server, you have multiple tasks, right? For example, I want to execute this query. This is kind of task, one task, right? It creates the task, and this task will be assigned to worker or thread. So this task will be assigned to the thread, and the thread will execute your query, right? So the thread will execute a query. So where the thread will execute the query, right? So the thread executes this task on CPU, right? So whatever thread which spawn to execute this query, it start executing. But where that execution happens, right? Somewhere execution happens. Otherwise, how you are getting the output, how the queries are executed. So the queries are executing on the CPU, right? So whatever CPU hardware that we have, so the query is executed on the CPU and using certain resources, right? So memory, IO, some CPU cycle, right? So everything will be considered as a resources which is using to perform or execute the task that we are creating. Let's say, for example, you are connecting to the SQL server, right? You are establishing a connection. So even to connect to the SQL server, it requires a thread, right? It requires a thread to connect, right? For example, if I take you to select star from sys.dm underscore OS threads, right? So this is the DMV where we can execute and get the thread. Um, right. So these are the threads which are spawning on, which are currently on the currently spawn on this particular instance, right? Whatever I'm executing, so these are all currently 82 threads which are spawned, right? So thread is a SQL Server terminology, whereas Windows terminology, we call it as a worker, right? So in a Windows terminology, we call it as a worker, right? So like whatever worker it is waiting for, and so you will have that information, right? Whatever queries which are executing at the SQL Server side. So each, I mean, we consider that as a task, and each task will be taken care by a thread. So the thread will start executing the task on the CPU, right? So on the CPU. So now we are going to talk about CPU that we have, right? So CPU is not that, so high CPU utilization. Yes.
Yeah, I just have a question on the threads. Are they fixed? Like I just ran the same query on my server, so I have 77 rows. What does it tell me about the system resource, this thread?
So uh, what do you mean? Like, so you executed the
So
steps and you see the
yeah,
same
yeah.
77?
Yeah, I have some like it shows me 77, but my question is what does it tell me from a resource check side or from a performance side? What does this tell me?
I will explain, right? So
Okay,
this is not telling anything, right? So this is just a
okay.
query to check, like, so what are all threads which are spawned. This can be a background threads, right? So whatever background processes which are running, so it can be a
Oh,
background thread
okay.
which is currently running on.
Okay.
Yeah.
Oh,
So
okay.
yeah,
Okay.
I'll
Okay.
explain that. Like, so this is not a
Okay.
what we will have to actually look into, right? So this is not limited
Right.
to these threads. But yeah, so we'll let you know. So the reason that I mentioned, because if going forward in the SQL operating system, we will talk about the threads, right? So if you don't have a context what is thread, so then you would not able to understand. So that is the reason I mentioned here the thread. Thread is nothing but a smallest unit of your execution. So whatever you execute this in the SQL server, so that will be taken care by a thread. That's it. So anything like even in this connect or background thread, or background operations, or even SQL user connections, so everything will be taken care by a thread, right? So that operating system, right? So we have a Windows operating system, that is where we have CPUs resides on. And on top of that, Microsoft has developed a concept called SQL operating system, right? So SQL operating system. Earlier versions, we use it to call UMS, user mode scheduler, right? So what does it mean by user mode scheduler? What does it mean by so SQL operating system? We are going to talk in this section, right? So what is SQL operating system? What is OS, right? If you recall the SQL architecture, right? So if you remember this components that we have, so this is where your user mode scheduler, right? So this part we are going to talk, right? Whatever we are processing here, so that will be executing on the CPU, right? So on the physical CPU. So how that physical CPU will be connected, right? So SQL Server and how physical CPU will be connected using the user mode scheduler. So we will talk why we need user mode scheduler, what will happen if you don't have a user mode scheduler, right? Right, so these are all we are going to discuss, like what are the scheduling basics, and what does it mean by preemptive and non-preemptive scheduling, and what is the UMS basics and troubleshooting, some EMS related issues, right? So we will talk about these. Okay, so for example, um we have a Windows operating system, right? So we have a Windows operating system. If you have a Windows operating system, why I need a SQL operating system, right? So why I need a different layer for the SQL operating system? Let's say Windows operating system I have, right, where we resides the CPUs. Let's say CPU 1, 2, and 3. So if you have a Windows operating system, and then why I need a SQL operating system, then why we need a dedicated operating system for SQL Server. The reason, let's say for example, you are spawning some threads or executing some queries, right? So if you're executing queries and let's say you don't have a Windows SQL operating system at all, right? So SQL operating system you don't have at all. What will happen? Let's say you are executing queries. Let's say you have 100 sessions created at the SQL Server side. So what will happen? These 100 sessions, so Windows doesn't know what are these. So Windows just know these are all 100 different threads. And these 100 threads will be spawned or will be allocated to these three threads, three CPUs. Let's say, for example, 35, 35, 35, let's say. Okay. These are all assigned, right? So in these threads, right? So 35, 35, 35 assigned. So it is a equal distribution. So in the Windows operating system, I cannot give a guarantee that the threads will be distributed equally, but let's assume that threads are distributed equally. These 100 threads are spawning on individual CPUs, right? And waiting in the queue. Let's say there are some certain queues and it is waiting in the queue. And what will happen? So this will executing on the CPU, one thread execute on the CPU, all cannot execute at the same time, right? So one thread execute on the CPU and then it will 34 threads, it's keep waiting on the other thread, on the CPU. So how long these are waiting is a quantum slice, right? So there is a quantum, right? 4 milliseconds of quantum. So as soon as the 4 milliseconds are completed, the thread which is currently running on the CPU will be come out of CPU and will allow other threads to execute, right? So this 4 milliseconds is called as a quantum, right? So quantum is 4 milliseconds. As soon as the 4 milliseconds are completed, then the thread which is currently running on the CPU will come out of CPU and will allow other thread in the queue to go ahead and execute. You might have a question, right? So I'm executing a query, right? So I'm executing a query, even it is like, so taking 1 hour, but it is not coming out of CPU, but it is still running like even 1 hour or 30 minutes or 45 minutes. How is that possible, right? That is because of SQL operating system. So we will talk that if 4 milliseconds, as soon as the 4 milliseconds is completed, then it will come out of CPU and will be waiting in the Windows operating system itself, right? It will be in the Windows operating system and will allow other thread to spawn and execute on the CPU, right? So it will allow other thread to spawn and execute. So likewise, so now 4 milliseconds is completed. So what will happen to my execution? Like 4 milliseconds, the query has not even completed, right? I'm just executing select star from table. It takes around 10 minutes to get the data, but 4 milliseconds, the query has not completed. So what will happen? It will write that context information into some internal structure. We call it as a context switches. So what does it mean by context switch? Whatever data, whatever thread context, it will write into some internal registry points. What we call it as a context switches. Switch is nothing but, let's say 4 milliseconds, then it will come out of the CPU and it will write that context information here. And when this thread loaded again into the CPU, then it will take the context and it will start executing from that point. You know what I mean? So as soon as it come out of CPU, let's say, for example, this completed 10%. The thread completed execution in 10, like the thread completed just at 10%. So if 10% is completed, then it will write that context information into the internal registry structure. And as soon as it gets a chance to execute again, it will take this context information and it start executing from 11th percent, right? So 11th stage, whatever. So it will not again rework, or it will not again start work executing from until the from start from 1%, right? It will start executing from the point where it left, right? So that is what we call it as a context switches. Now, so when this thread get a chance again to execute on the CPU, so thread get chance only after this 35 threads are completed. So what does it mean? Uh, it is kind of a queue. Let's say this is your CPU and this is your queue at the Windows level. So the queues are same at so SQL and Windows, right? So but for now, just understand it is a Windows operating system, right? So SQL, there is no SQL OS. It is just a Windows operating system. So I have a one CPU and I have around 35 threads spawn on the CPU to execute. These 35 threads will be in a so first in first out basis, right? FIFO. It follows that FIFO. So whatever threads which are first coming in, so it will start executing. Let's say, for example, here I have 1, 2, 3. Likewise, I have 35 threads in the queue. Now, this first thread will start executing, and this after 4 milliseconds, this will go out of the CPU. It will write that context information, whatever, wherever it is left, and then this thread will go back to the queue, end of the queue, right? Whatever threads which are currently running, it will come out of CPU after 4 milliseconds, and it will write that context information, and it will go back to the end of the queue. So next thread will come and execute, and after 4 milliseconds, it will write here and it will go. Likewise, it will be noisy, right? So you are keep every 4 milliseconds, so you are keep coming out of CPU, and you are writing that context information here. So what is the drawback in this? This is the Windows operating system. Let's assume that you don't have a SQL operating system. So what is the drawback here? One, you are doing a high context switches. Context switches. If you're doing a high context switches, you have a high threads on the queue, and you are keep moving here and there from the CPU. The threads we are moving from in and out, right? So you are doing a high context switches, right? So you have a high delay or wait time, because all these threads are waiting its time, and it is trying to execute, right? So until the first thread is completed, so the 35th thread is waiting for very long. Like likewise, if after 4 milliseconds, if it is go back to the last or end of the queue, so and this thread, the end of the queue thread, will have to wait until the all other threads completes its execution, right? So high wait time, right? So the main problem that we have is your context switches. If you are performing a high context switches, it can leads to high CPU utilization, because you are writing context information into some internal registry structure that also requires some CPU cycle, right? If you keep writing into the context, that will leads to high CPU utilization. So if you notice any high CPU utilization, and if you don't have any um, queries or anything, maybe context switches one way you can validate. How can we validate? So we have a performance monitor. For example, if I go here, perform, we will talk about the performance. So just for your information, if I go here, if I take this, processor. Mm, o- okay, process. Process. Hmm. Somewhere it would be there, but yeah, I'll show you that, so after maybe sometime, because somewhere I couldn't find that context switches that we have. Okay, that is not needed, that is not mandated, but I'll show you that in a bit. Just bear with me for some time, like I'll show you that. So that is how that it impacts the performance, right? So like we are spawning every thread, right? Whatever threads which are spawning, if it is a 100 thread mission, 100 threads. Let's say, for example, what will happen if it is 1,000 threads, right? So let's say you have a high CPUs and you have 1,000 threads spawning at the same time, right? To perform some different operations, right? So this will be divided across multiple CPUs that I have, right? So if that is the case, again, multiple threads will be spawning and all will be waiting in the queue, and you will have every 4 milliseconds, it will keep coming in and out from the CPU. That will write into the context, and you will see a context. You will see a high CPU utilization because of context switches, right? Now, so that is one problem. You will have the high number of context switches with the Windows operating system. Second one is, so Windows operating system is the Windows level, right? So SQL is not only one process which is on the Windows machine, right? Let's say, for example, there are other processes, right? So process is nothing but application which you installed on the computer, right? So that is what we call it as a process. Process is nothing but an application. It can be anything, right? It can be a notepad, it can be a PowerShell, it can be a SQL server, or it can be Power BI, or any application which is installed on the Windows machine is called as a process, right? Process. So SQL server is also a process which is executing on the machine, which is installed on the computer, right? So now I have some other process. Let's say, for example, analysis service or SSIS installed. So to perform that SSIS, that also requires some threads. Every process that we execute, it needs a thread. It executes using a thread, right? Anything, even notepad, that is using a thread, right? So anything you can consider, it uses thread. Now, so I might have some other processes on the computer which executes. Then that those processes also spawning on the same CPU, right? So then it will be in the queue and we'll wait for all threads to complete, and it will just doing the same thing. Every 4 milliseconds, it will come out of CPU and it will write a context and it will load the context and perform the execution, right? So that is the second problem. Suppose if you have a multiple applications or different applications on the same computer, that also creates threads and it will be in the queue, right? So that is one thing, right? So Windows, you will have a multiple processes. Now, so that is one thing. Second thing, let's say, for example, whatever Windows thread which is executing, whatever Windows thread which is executing doesn't know whatever threads which are there in the queue is SQL thread or Notepad or PowerShell, or it is whatever it is, right? It is just considered as a thread. Let's say Windows has a high priority thread. Now Windows is executing a high priority thread. So high priority is nothing but, let's say you're executing a select statement, SQL query. SQL side, we considered every thread is same priority, right? So let's say SQL side, we are executing one query, and there is a Windows background thread, which is a highest priority. Priority is nothing but, let's say, whoever has highest priority, those will precedence. Those will have a precedence, right? The same thing, Windows some has a highest priority. Let's assume if it is a highest priority thread, what will happen? So the thread which is currently executing on the CPU with respect to the quantum 4 milliseconds is completed or not, the thread will be kicked out of CPU, right? I'm talking only the Windows operating system area. So it will be kicked out of CPU and it will start executing the highest priority thread, right? So simple way, if it is a highest priority thread, whatever threads which has the lowest priority in the Windows operating in the on the CPU, that thread will kick out of CPU and will allow other thread which has a highest priority to execute on the CPU, right? So this is the Windows content, Windows behavior. So what will happen? So in this case, if a highest priority comes in, whatever threads which is coming out of CPU with respect to whether the 4 milliseconds quantum is completed or not. So if it is not completed, again, you will have a more context switches, and whatever the execution time would be delayed because you are coming out of CPU, right? If you come out of CPU, then the query would not complete, would not be executed further. So it will have to wait until the queue is clear, right? Even if it's come out of CPU, it will be placed in the end of queue, right? So even let's say, for example, even one milliseconds completed and high priority thread comes in and kick this thread which is currently executing, then it will be in the end of the queue, right? So that is the behavior of the Windows operating system. So Windows operating system is a priority driven, right? So whatever high priority threads comes in, so that will allow thread to execute, and whatever the lowest priority threads comes in, so that will be kicked out of CPU, right? So that is what priority driven means, right? So priority driven, let's understand. So preemptive versus non-preemptive. So preemptive, that is priority driven, and second preemptive, let's say Windows uses a priority driven. That's what I was talking, right? Windows uses a priority driven and a preemptive scheduling algorithm. So preemptive scheduling algorithm, because we follow the quantum behavior in the Windows mission. So 4 milliseconds, you'll have a quantum. As soon as the 4 milliseconds quantum is completed, it will come out of the CPU preemptively. Okay, preemptively, it will come out of the CPU. Once the quantum expires, threads are scheduled off and must wait for NT to schedule them again. NT is nothing but your Windows operating system, and must wait for them to schedule again. So I was talking in the queue, right? As soon as it is came out of CPU after 4 milliseconds, it will be in the queue and will wait for the all other threads completed its execution, right? So that will be potential for threads to be preempted before the quantum expires by high priority threads, right? That's what I was talking. So as soon as a high priority thread comes in, so the thread which is currently executing and it is a low priority thread, it will come out of CPU preemptively, because preemptively it will come out of CPU and will allow other thread to execute, right? So that is what the behavior of the Windows operating system even till today. The Windows operating system even till today. Now the behavior we cannot change. The Windows operating system behavior we cannot change. What we can control, so we can control from our SQL Server side. So that is where we have a wrapper called UMS, user mode scheduler, right? So user mode scheduler. So we have a just a so wrapper on top of your Windows operating system, we have a SQL operating system. Or earlier versions in 2000, we used to call it UMS. Starting from 2005, SQL Server, Microsoft, product team and developer. So, created as a, coded or implemented as a SQL operating system, right? So now, what is SQL operating system and why we need a SQL operating system? So if you simply mention UMS is a thread pool. So what does it mean? I'll try to explain here so that I will go to the PPT. Let's say, for example, this is your SQL layer. This is your Windows layer, kernel layer, or whatever. Windows OS. It is your SQL Server. SQL Server. Now, in SQL Server, so let's say, for example, you have a 3 CPUs or 4 CPUs, whatever it is, right? Physical operating system, I have 4 CPUs on my computer, right? 1 second. So physical operating system, I have a 4 CPUs on my computer. So if I have a 4 CPUs here on the system, then what will happen in SQL Server? So SQL is a capable enough to have this logical layers as well as per the CPUs that I have. So logical CPUs as in, so we call it as a schedulers. So it will divide, so it will be converted as a logical CPUs in the SQL Server, whereas these logical CPUs will be mapped to the physical CPU. So what does it mean? So if you install SQL Server on a 4 CPU mission, so SQL Server, you will have a SQL Server internally understand, okay, there are 4 CPUs. I can see 4 CPUs. SQL Server can see 4 CPUs. So logically, I will divide into 4 different CPUs, logical CPUs. So this is what we call it a SQL OS, SQL operating system. If you have a SQL operating system, then SQL operating system understands, okay, there are 4 CPUs physically. Then logically, I create SQL Server to understand. So logically, I am creating 4 CPUs. And these CPUs will be individually mapping to each other, right? Let's say, for example, this is one CPU, this is another CPU, this is another CPU, this is another. So logically, so it will be created a scheduler. So we call it as a scheduler. Scheduler 1, scheduler 2, 3, 4. These individual schedulers will be mapped to the CPU, physical CPU, right? So I'll just show you the schedulers here. If I execute, select star from sys.dm underscore os underscore schedulers, select start from sys dot okay, so I will explain this threads. Hope this is visible. Let me clear up. Right, let's say this is the schedulers that I have. So hidden online or whatever the hidden, so ignore those hidden because it is not visible to the SQL Server or Windows anywhere, like, so it is not visible. It is just a SQL Server has this hidden schedulers to see some internal or background threads to execute, but you can ignore them. We don't have anything. So currently I have, if I go to the task manager, performance and CPU, I have four virtual processors, four CPUs that I have, right? So one, two, three, four. So four CPUs I have. So if I have a four CPUs, what I was talking, logically, SQL Server will have a four schedulers. So in SQL Server, we call it as a scheduler. In the Windows operating system, we call it as a CPU, right? So here we have a four CPUs, right? So scheduler 0, 1, 2, 3. So this scheduler will be, I told you, this scheduler will be mapped to the CPU, right? So this is the mapping, one-to-one mapping. Zero, scheduler 0, CPU 0, 1, 1, 1, 2, 2, 3, 3. So likewise, it will map the scheduler and the CPU to execute. Let's say, for example, you have exhausted all the schedulers are busy, or you have exhausted the connection. So you would not be able to connect. There is a one more scheduler called scheduler 64, or not scheduler 64, because basically it is just a one way, right? So you should be able to establish a connection using a DAC, dedicated administrative connection. So we will talk that later. But if you have a, or if you have four CPUs on the computer, so all these four CPUs will have a logically, we consider as a schedulers, right? So SQL Server will use that as a scheduler. So if it is scheduler, if you have a schedulers, and if all the schedulers are occupied, are busy, and you were not able to establish even a single connection because you have all the schedulers are busy, then you can open a connection using dedicated administrative connection, DAC, because it is using a different scheduler altogether. So it is not within the four CPUs or something. It is just a background scheduler it uses, and able to establish a connection to the SQL Server. So yeah, leave that part, like if you're not clear, but that's okay. We will talk that later. But you have a four CPUs, and you will be connecting to the SQL Server using one of these CPUs that I have, right? So this is the logical processors, right? Logical schedulers. Now I have, let's say I have four CPUs, anything, something, right? So I have a four CPU schedulers, and it will be mapped to one to one. The scheduler and CPU will be mapped to one to one. Now what will happen? So you have 100 threads. This is SQL operating system. This is the Windows operating system. You have 100 threads, and this 100 threads, again, it will be distributed in a round robin fashion. What is that mean by round robin? So one thread will spawn here. So next one will be here. Next thread will be here. Next thread will be here. Likewise, this 100 will be distributed equally among all the four schedulers on the SQL Server, right? So you will have this 25, the 25, 25, and 25. So earlier, even Windows operating system, we did the same thing, right? Even Windows operating system, we spawn everything here. We spawn everything here. We spawn everything. We are, so spawning everything here on the Windows scheduler. Now, SQL side, SQL layer, we have a assigned these many in the to a specific scheduler. Now, what SQL Server does, SQL Server will schedule them on the CPU. So that is what we use SQL operating system. SQL operating system, what it does, it will start scheduling the threads. Instead of spawning all the threads on the Windows operating system, SQL, what it does, it will allow only one thread at any point of time. So only one thread, it will spawn, it will go ahead and execute on the CPU. So remaining 25 4 threads which will be in the SQL operating system. So it will not spawn all threads on the Windows operating system. It will allow only one. It will schedule only one thread out of SQL OS to the Windows operating system to start executing the thread. So what are we eliminating here? So we are eliminating high context switches. High context switches because you have only one thread. The other threads which are not spawning, like other threads are still there in the SQL operating system layer. So you are spawning only one thread on the Windows operating system. You are scheduling only one thread, and the thread will start executing on the CPU. So in one thread which start executing on the CPU. So when this thread will go back to the SQL operating system, there are certain conditions. One, if the thread needs some resources, let's say for example lock, the thread needs some lock, page lock, let's say anything, right? If the thread needs some locking, I'm not going to specify anything, but yeah, thread is requires some resource, then it will come out of CPU. Then it will come out of CPU and it will be going back to the SQL operating system. Or if the thread is complete, if the thread completed its execution, whatever time it took, that is secondary. So once the thread is completed its execution, it will come out of CPU and it will be going back to the SQL operating system. Third point, third point. So in like how long this will continue executing? So how long this continue executing? Let's say this is not waiting for anything, and there is no execution is not yet completed. How long it is keep running on the CPU? So it should allow other threads which are in the SQL operating system to execute on the CPU, right? So then Microsoft developer, what they have done, if the query is running unnecessarily and overwhelming complete CPU, then you should come out of CPU. That is what we call it as a yield points. Okay, yielding is nothing but the thread which is currently running on the CPU should come out of the CPU. That is what we call it as a yielding, right? So thread yielding. So Microsoft developer in the Microsoft code, SQL Server.exe code, they have set certain yield points. So if your code met that yield point, right? So whatever query that you are executing, if it met that yield point, then the thread which is running on the CPU should come out of CPU, right? So if it met yield point. So these are the scenarios which I could think of, the thread which come out of CPU, right? So whatever threads which are running on, it will come out of Windows operating system. But you can think, right? What is that 4 milliseconds here? So this 4 milliseconds is just a Windows concept. It is not a SQL related. So as soon as the 4 millisecond is completed, it will be, let's say here also the quantum happens. Here also the quantum works. But what will happen? How the quantum works here? Let's say thread is currently running on the CPU. As soon as the 4 milliseconds is completed, this thread will check any of the other threads which are waiting in the Windows operating system. SQL OS you have, so definitely there won't be any SQL threads in the Windows operating system queue. But there are chances you can have different applications altogether. Let's say, for example, Notepad. So Notepad, it spawn one thread. Then what will happen? The thread which is currently running on the CPU, it will come out of CPU after 4 milliseconds, and it will allow the notepad thread to execute, and it will write the context switches somewhere, right? Context. And then if notepad is completed, it will come out of CPU and it will allow SQL thread to execute, start executing. So here we are reducing the context switches because you will not have more threads in the CPU. On the Windows CPU, Windows operating system, right? So that is the reason we always suggest to have a dedicated mission to the SQL server. If you don't have a dedicated computer to the SQL server alone, you will start seeing that high number of threads spawning at the Windows operating system. Even you have a SQL operating system, there are different processors, right, can take this CPU. Right? So that you have the same behavior, same concept at the Windows operating system. So SQL operating system, by just we are wrapping around and you are improving the scheduling mechanism. So scheduling is nothing but SQL will take care of the scheduling. So why would I give a Windows operating system to schedule my threads? So I'm a SQL server. So why would I give Windows operating system to schedule my threads, right? So instead of that, SQL will schedule on its own. That is where SQL operating system came here. SQL operating system, whatever threads that we have, it will spot one thread to execute on the CPU. And remaining threads will still be in the queue until and unless the query completes its execution, right? Or until the query come out of Windows operating system. So it can be a thread, it can be some resources it needs, or it can be the query completed its execution, or it can be some yield points which Microsoft developers has set in the SQL Server.exe, or it can be the thread, the query which application team is executing, they might have cancelled, aborted the cancel query, or whatever query which is cancelled or killed. So that will go out of CPU again, right? So then it will go back to the CPU. Let's say, for example, that we will talk that later, but this is a high level understanding, right? So that is what I would have it here. So UMS is a cooperative user mode scheduler. So I will tell you why we call it as a cooperative. Let's say, for example, the thread which is currently running on the system, on the CPU, Windows operating system. So there are few threads, SQL operating system that we have. So how SQL operating system will understand the thread which is currently running on the CPU will come out of CPU, right? So a thread 1 is currently running on the CPU. So thread 1 is currently running. How SQL operating system understand the thread 1 is coming out of CPU and I'll have to schedule next one? SQL operating system doesn't know. So that is the reason the thread which is currently running on the CPU, it will give a signal to the thread which is in the queue. SQL operating system, it will give a signal. So the thread which is currently running on the CPU, right? So that will give a signal to the thread which is in the which is in the queue at the SQL operating system, so that the thread can execute, can spawn on the Windows operating system. That is what it is, a signaling. It will give a signal. So that is how, that is why we call it as a cooperating scheduler. So it will be cooperating, it will be cooperate with the scheduling, whatever threads which we have and whatever threads which is currently executing, it will cooperate with each other and it will start executing on the CPU, right? So this we call it as a signaling. So it will give a signal and so the next thread which is in the CPU, which is in the SQL OS, will start executing on the Windows operating system, right? So this is why we call it as a cooperating scheduler. So cooperating user mode scheduler. Okay, simply put, is a thread pool. So I was talking, right? So whatever threads 25, it will not immediately spawn every 25. Only one thread will go and execute on the CPU. right? So that is why we call it as a thread pool. Allows SQL Server to smart about when it waits, right? Allows SQL to be smart about when it waits, right? So it will wait for the signal to receive from the thread which is currently on the CPU, right? So it know, right? So SQL Server to be smart enough to understand when to schedule, right? So allow SQL specific management of CPU time. So it is completely a SQL related, right? So it knows how to manage the CPU and how to schedule threads and all. So UMS is a logical, not physical. That's what I was talking, right? It's just a wrapper on top of Windows operating system that I have. So it is a logical. So we call it as a scheduler, a logical scheduler. We did not change anti-scheduling behavior. We just manage it. That's what I told, right? It is, we are not changing the behavior of the Windows operating system. We are just creating a wrapper on top of the Windows operating system so that SQL Server understand how to schedule our own threads, right? Instead of letting Windows operating system to take care of scheduling, so SQL operating system will take care of that. That is what here. So if you, I will go forward, like if you have any questions or anything, just stop and ask me for clarification. No issues. Okay. So the main
Sorry,
yes.
the quantum, right? Is it applicable to
No,
SQL thread?
no, that's what I mentioned, right? So it is quantum is only at the Windows operating system. So as soon as
So
4 milliseconds
so
completed, yes.
so a thread from SQL OS that goes into that is now running on the processor,
Mm,
we continue to run
correct.
until it's completely like okay. So everything is completely done before it's yield, right? It
Correct.
doesn't like if the if the SQL thread is running and the Windows has a thread, right? It
Mm,
will not yield, right?
mm.
It won't yield after 4 milliseconds, even though
So
there is a
it will
thread
not
from
go
Windows
back to the SQL Server. It will be yielding within the SQL Server itself. So let's say for
within the Windows.
Windows kernel, yes, Windows operating system.
Okay, I see.
Yeah. So one of these should be reason for the thread come out of come out of Windows operating system to SQL Server. So either thread needs some
Mhm.
resources. So if thread is required some page to be available, so that cannot be running on the CPU, right? So
Mhm.
it should come out of CPU and go back to the SQL operating system. Like execution completed. Let's say you are executing select query that is completed, then it should come out of CPU. Our third point is yield point, right? So yield point is something which you cannot see, so at the SQL server, but it is at the SQL code level. Microsoft engineers has developed some yield points. Let's say, for example, once it met that yield point, like let's say this is one code yield point and another code yield point, another one yield point. If this yield point it met, then SQL Server decides, okay, there is some flaw in that, there is some issue with the codes, and then I should go out of CPU. Then if it is second yield point here, so likewise, if it met that yield point, it will come out of CPU. So that is where you might heard like non-yielding scheduler. If the thread is not even yielding, and there are chances that could be a bug at the SQL server, because ideally it should meet that yield point and come out of CPU. If it is not yielding out of CPU, there are chances the code level bug, or the yield point is not properly defined or not properly set, or SQL server is not able to identify that in the yield point code. So that is where we mostly, if the thread is not yielded and it is completely keep running and you generated a non-yielding scheduler or non-yielding dumps, then that is majority of the cases the thread might be that might be a bug at the SQL server side code level. Right?
Okay, thank you.
Sure. Mm. Right. So next, the reason that we have UMS, user mode scheduler, is to control this. All I talked already, just I'll give you a high level. Control which thread should run from SQL Server, right? We can control how the threads would be executing. We try to run one thread per CPU, but there are exceptions, right? One thread per CPU, right? Suppose if you have a parallelism, so you will have multiple threads spawning to execute the same task on different schedulers. So that is the exception that it is talking about, right? So next one, priority is irrelevant. So what does it mean by priority is irrelevant? Because we don't follow the priority mechanism, right? So whatever threads which are coming in, all threads are in the same priority, right? So if you go back to the SQL Server error log, so how can you read the error log, right? So you have different methods to get the error log. One is go to the file explorer and you can read the file explorer and open that error.txt, or you have something called SQL Server logs, right? So from this SQL Server logs, you can identify the SQL error log like management and SQL Server logs. You can read the SQL error log, or my way of so reading the error log is sp underscore read error log, right? Or you can use xp, whatever it is, extended stored procedure or stored procedure, you can use to read the error log, right? So this one, you have grid format or text format. So I preferably go with text format so that I will get the error log information. This is the error log I will have. So if I take that down, right? So you will have the priority information. 1 second. So I have so much, right? Like either I can copy this to the notepad and filter with whatever string that I have, or you can just use that filter here as well. 0, 1, comma. So what does it mean? 0 is nothing but your SQL error log. If it is a 1, it is a SQL agent, right? So 0 I'll take, and 1 is for the first error log I'm looking at. So 2, 3, 4, whatever it is, the max, so whatever max limit that we have, so that is where you can define that values, right? So this is how you can get the info, right? So if you see here, SQL Server is starting at normal priority base, right? Priority is nothing but like we have that low priority, medium, or high. So there is a different so stages of the priority. It is not something that like 1, 2, 3. You will not have that, right? So if SQL Server is defined that normal priority, that is at 7. No, priority is 7. That's it. So SQL Server is all threads are under the normal priority, right? Until and unless you define that high priority execution. Let's say, for example, you're executing query and you started seeing some deadlocks and all, and if you want to define the deadlock priority is 7, deadlock priority is high. If you define the deadlock priority high, the deadlock priority which is set to high, that will precedence over other thread, right? So that is just for your information. We will talk about deadlock later. Don't worry about it. But here, if you see, SQL Server is a normal priority, that is 7 for every execution that we are executing, right? So that is a priority irrelevant. So there is no priority. So what will happen if you have a priority thread? So priority thread, so if a priority thread spawn, then it will start executing on the CPU and it will kick out of the execution threads which is currently executing on, right? Let's say this is your thread. It has a low priority 7. Let's say the thread which is currently executing with a priority 7. Let's say high priority thread comes in. Let's say, for example, 15 priority or 32, whatever, like priority that I have. So this has to execute. So it will go and execute, start executing, and this will be kicked out of CPU, right? So that is a priority driven. But SQL Server, every thread is the same priority. So one thread will not be kicked out of another thread because of the priority concern, right? So priority is not a priority is irrelevant in the SQL Server operating system. That is one reason. So Windows operating system, there is a priority driven, right? If the high priority thread comes in, so Windows operating system will allow high priority thread to execute, and it will kick out of CPU. The low priority thread will kick out of CPU and it will go back to the queue, right? So, but in SQL Server operating system, the design goal for UMS, priority is irrelevant, right? With respect to whatever priority, so the threads will be spawned and execute on the CPU, right? Priority as far as scheduling is concerned. The next one, make a better decision when we allow OS to schedule our threads, right? Just some construct to make a better decision when we allow OS to schedule a threads, right? So instead of we let operating systems schedule, we are scheduling a threads so that we are making a decision, right? So when to execute what threads. So SQL Server side, we are making decision and scheduling a threads individually to run on the CPU. So we are not letting Windows operating system to schedule our threads, right? So that is the one of the design goal that we have. So avoid causing a thread to switch into kernel mode whenever possible, right? So it will avoid the thread to switch into kernel mode, right? So that is what we call it as a context switches. So context switching everything like it is happening in the kernel mode itself, right? We are avoiding that because we are spawning only one thread at any point of time. We are not spawning. Spawn is nothing but so let thread to execute on the CPU. That's it. So just a terminology that we use. So spawning, we are just let the thread to execute on the CPU. At any point of time, only one thread will be executed on the CPU. So we are avoiding the context switches or switching in the kernel, whatever. Support asynchronous IO. So asynchronous IO, we will talk about the IO, but asynchronous IO, let's say, for example, you posted some IO operation and you are not waiting for that IO to be completed. For example, backup, or so take an example of backup. So if you post a backup, so it performs asynchronously. So to process that pages, whatever that we have on the disk, right? So that is asynchronous process. So we are not waiting for the backup to be completed. So your database is accessible, your threads should be able to access the database, everything can be performed, right? So that is where the asynchronous process happens. Asynchronous. If it is a synchronous, what will happen? The data has to be waited, right? So while taking the backup, you would not be able to access, right? So that is where the asynchronous, it supports a asynchronous IO. So Windows operating system, mostly it is a synchronous IO, which has to wait, right? But SQL Server, it performs a asynchronous IO. Another example is, let's say, for example, you are doing a checkpoint. So even if you are running checkpoint, if checkpoint is happening, it writes the pages asynchronously to the data file. So we are not waiting anything to checkpoint to be completed. So checkpoint, it writes the pages asynchronously into the data file or lazy writer. So anything you can consider, it is an asynchronous process which performs on the SQL Server, which performs and write asynchronously, where we don't wait for the IO operation to be completed, right? So that is the design goal that we have to, so Microsoft developers, based on these design goals, they have developed the UMS, user mode scheduler. Right. So what are the few terminologies that we have? We already talked quantum. The time slice, a thread is given to run by a Windows scheduler. So you have a Windows operating system. So you have a quantum slice, 4 milliseconds, then it will come out of CPU, Windows level. So Windows creates the illusion that all threads run concurrently by partitioning the time each thread is allowed to run into time slice called a quantum. That is a 4 milliseconds. It hands quantum to thread in a round robin fashion. So round robin fashion, so it will give a quantum to each thread, right? So whatever threads which in the queue, so it will go first thread, it will go and execute. And after 4 milliseconds, the next thread, like that, it will give you a quantum of 4 millisecond slice of each thread to the each thread in the queue. So context switches, this also we discussed. So saving info for old thread and loading info for new thread, right? So let's say you are executing a thread which has completed 90%. And if you yield out of the CPU after 4 milliseconds quantum, if the thread is coming out of CPU, that context, the execution information has to load somewhere, right? So then the next time if the thread started executing, it can load that information and start executing from where it left its execution. That is 91%. It should start executing the thread, right? So that is the context switches, right? Process and threads, right? So this already we discussed, like process is nothing but each application that we install on the computer, we call it as a process. So the process as execution unit, right? So process you'll have a multiple task in the process, and each task will be assigned to one thread, right? Threads as multiple execution context in a process, right? So you have a process. In this process, like let's say for example SQL Server process, in this process you'll have a multiple task, and each task will be assigned to one or more threads. So the threads are actually executing your task that you are executing, right? Key takeaway: processor is just a container. So processor, like processor. Process is nothing but the application we install on the Windows operating system, whereas processor, we call it as a CPU, the physical CPU. So that is what we call it as a processor. Let's say, for example, I have 4 CPUs. We call it as a 4 processor mission. So if I have 4 CPUs, we call it as a 4 processor computer. If I go here, performance, so processor, so this is what it is, virtual processor. I have 4 processors on this computer, right? So the each processor, we call it as each CPU, we call it as each processor, right? So that is what it is mentioned here. Processor is just a container which provides infrastructure for thread to execute, right? So that is what we all know, right? So the CPU is like, you can consider that infrastructure, right? So whereas the threads go and execute on the CPU. So this will give the so the infrastructure to execute the threads on the CPU, right? So that is what the processor is nothing, uh, not something, so that is actually doing, right? It is just a container which allow threads to execute, right? Process does not execute the whatever process that I have. SQL Server doesn't execute anything. SQL Server will have multiple threads, and those threads will execute the task that are created inside the process, right? So that is what it is. Process does not execute or run. Rather, thread associated with the process run on processor. Whatever threads which are spawning in the process, that will start executing. Those threads will start executing on the processor. That is what we have. Yeah, this is all we discussed. Like a process as such contains several individual tasks. Like this, we'll have a several individual tasks that may or may not be depending on each other, right? Definitely, it may or may not be depending on each other, right? And this makes us to do a design change, whatever, right? So this will not be, it might or might not be depending. It doesn't matter whether it is depending or not. You have a multiple tasks created and multiple threads will be spawning to execute your tasks. Okay. This is the terminology again. Same thing that we discussed. Like a thread is a unit of execution within a process. Multiple threads can exist within a process, right? So you can have multiple threads. That is true. Multi-thread process, right? Each is given small amount of processor time. Wait while other threads to execute, called a scheduling. SQL Server uses OS threads to perform its work, right? SQL Server uses OS threads to perform its work, like it is internally converted that into thread, into worker, whatever it is, called as a worker threads, right? Dedicated thread exit. Most are in the pool of threads that SQL Server uses to process user requests, right? Worker threads. Right. So whatever threads which are created, like it is, we call it as a worker threads in the SQL Server. Mm, 1 second. Right. So we have some thread scheduling. SQL Server has its own thread scheduling, right, called a non-preemptive scheduling, and is more efficient than Windows scheduling, right? So performed by the SQL operating system layer of the storage engine. That's all we discussed. So how the scheduling threads will be scheduled and all. So each processor, right? So each processor, that is what we call it as a physical processor, has a scheduler. The reason we mention logical or physical, because if it is a virtual machine, we call it as a logical processor. If it is a physical machine, we call it as a physical processors. For example, if I go task manager, CPU, we call, we defined as a logical process, but this is actually a physical machine. Whereas if you go back to the here and you will have that virtual processor, this is the virtual machine. So here you see that virtual machine is yes, yes, this is a virtual machine. So you will have that virtual processors. A scheduler is responsible for managing the execution of work by threads, right? So we define, so scheduler, right? So we define a scheduler at the SQL server side, and it will manage that execution of the threads, right? At the SQL schedulers. So scheduler exists for user threads and if for internal operations as well, right? So let's say internal operations as in, for example, checkpoint. That is an internal operation, or lazy writer. That is an internal operation, right? So likewise, you have some internal operations that will be using a thread, right? So the same behavior as SQL Server user threads. Use sys.dm underscore voice scheduler DMV to view schedulers. That I have shown you that how to check that scheduler, right? Sys.dm underscore voice schedulers, where we have, right? So if I just filter where status equal to visible online. So you can see that what are the threads which are on visible, and the information you can see here, right? If you see here, the context switches. So you have that context switches here. So this is where this is starting from SQL. This whatever matrix that we see. So this, since the SQL is restarted, right? So since the SQL server is restarted, preemptive context switches, right? Preemptive context switches, context switches is nothing but the terminology is same, right? So context switch is nothing but It is coming out of CPU and going back to the SQL operating system. Preemptive context, preemptive switches, right? So preemptive switches is nothing but how many times the thread is preempted from the CPU, right? So these are all total on that particular CPU, right? You can have this understanding like current worker count, how many workers are currently spawning, right? So I told you equal distribution. So this is all equally distributed almost, right? Around 14, 15 threads on each CPU. And how many are active, right? So these are all active. So what is the work queue, whatever, like, so you'll have this information from the scheduler itself. That is what it is. Now, so I mentioned this, right? So the threads will be in this 25 threads will be in the queue. What are all queues that we have? Sorry, what does it mean by queue? Let me clear this up. Let's say I have two CPUs, right? Each CPU, I'm talking only the SQL operating system. Here at this point, I'm talking SQL operating system. Each CPU will have a separate queue. So in this queue, what are all will be in the queue? So one is runnable queue, waiter queue, timer queue, IO list. I will tell you what are these. IO list. Let's see what I can see there. Okay, whatever. Let's say this is this yeah, you can consider this as a queue, right? So you have a CPU and UMS scheduled, right? So in this UMS, individual UMS schedule, UMS or SQL operating system, you have a different queues, right? It is not completely defined, but these are all few queues that we have. Now, so let's say this is a what I mean. It has different queues that we have, right? So let's say, for example, this is an runnable queue. This is a timer queue, time waiter, whatever. So whatever threads which are currently executing, so all threads, whatever threads currently scheduling, every thread should be in the runnable queue. So runnable is nothing but, okay, so my thread has all the resources which requires and ready to run on the CPU. That's it. So whatever threads which are spawning by the SQL operating system to the Windows operating system from the threads which are there in the runnable list, runnable queue. Let's say I have 10 threads. The 10 threads should be in the runnable queue. Then only the threads will get a chance to execute on the CPU. Now, I was talking, let's say the thread which requires some resources. So the thread which requires some IO operation, the thread which requires some page or lock or some backup to be happen. So whatever it is, if it is waiting for some resource and if it needs to wait for some resources, it should come out of CPU. That's what I was talking. So where the thread will be placed, if it comes out of CPU, where the thread would be placed, right? The thread will be placed in the waiting queue, right? So whatever threads which is coming in, so it needs some resources so that it has to wait for some resources. Then the thread will come out of CPU and will be placed in the waiter queue of that particular scheduler. So now, as soon as the waiting resource has granted, let's say, for example, it is waiting for some memory. The memory has been granted. So if the memory has granted, then it will go back to the runnable queue, end of the runnable list. So end of the runnable queue. So I have a 10 threads in the runnable queue. This thread, which it got the wait resource, and it will be in the 11th in the list. So then it will wait for this its chance to start executing on the CPU, right? So it start executing on the CPU. But whatever threads which are in the runnable queue, that those threads only will start executing. Let's say it posted some IO operation to perform anything, backup IO or some IO completion, right? So some IO related network IO, anything which is posted some IO operation, then even that thread cannot keep running on the CPU until it gets the IO which is requested for, right? It should come out of CPU. Where that will be placed, there is another queue called IO or IO list. So as soon as the IO is completed, there is a IO completion port, right? So IO completion monitor, it will track that whether IO is completed or not. And then as soon as the IO request is completed, then it will be sent it back to the runnable queue, end of the runnable queue, right? Everything that we are executing should be available in the runnable queue. So once it is in the runnable queue, SQL understand, okay, the threads in the runnable queue and not waiting for any waits. It is ready to run on the CPU. Now there are some background threads. Let's say, for example, checkpoint, lazy writer. So these are all executing in certain intervals, right? Let's say, for example, checkpoint happens on 60 seconds, every 60 seconds. Lazy writer executes like whenever there is a memory pressure or whenever there is a memory changes and all. Or if there is a monitor, scheduling monitor or resource monitor every 5 seconds, right? So some background or some internal scheduling, so scheduling threads which will be in the timer queue, timer list. So as soon as the thread is ready to execute, it will go back to the runnable queue and it will start executing from there, right? So that is how the scheduling behaves. Now, so whatever threads which are in the runnable queue, only one thread can spawn and execute on the CPU. So the other all threads will be marking as SOS scheduler yield. SOS scheduler yield. So what does it mean by SOS scheduler yield? SOS is nothing but SQL operating system and waiting for this scheduler to yield, waiting for whatever thread which is running on the CPU to be yielded to schedule the next thread, right? So if you notice that SOS scheduler yield, the thread is in the runnable queue and ready to run on the CPU, but it is waiting for this to be given. The signal has to be given by the thread which is currently running on the CPU. So you might ask, I notice that SOS scheduler yield frequently, right? So if I see that SOS scheduler yield frequently, would it be an issue, right? So if you notice that SOS scheduler yield, that might not be an issue. But when the issue would be, so when we have to focus on, let's say the thread is currently executing on the CPU and is not giving, so signal for some time. So if the thread which is currently running on the CPU is waiting for high signal time, so then you can understand, okay, so this query, this thread has this weight, SOS scheduler yield has highest wait type and signal is very high. Signal time is very high. Then why that signal time is high? Because some other thread or some other query which is currently executing on the CPU and taking more time. That is where you'll have to fine tune the query. But here our understanding, so if it is in the runnable queue and it is marked as SQL scheduler yield. So all SQL scheduler yield is not an issue. Let me show you this. Okay, so if I take here new query, so it tells that what are all, so top weights that I have, right? So it gives that, like we will talk about the weights, like for example, signal wait time. So signal wait time, how much time it is waiting for the signal to be, so what is the wait, what is the time it is waiting to get the signal, right? Signal wait time. So that is what you see, that signal wait time. We will show, I just wanted to show you. So top wait times, no. Okay, sequence is a current waiting task. Okay, so we will talk about the wait types, like for so that is where, like, I don't want to mention here. So we have I would say, let's say for example, okay, whatever. So let's start from where wait type equal wait type, like, so you can have this as well as scheduler. This is just a frequent one, right? So if you have this wait type on the computer, and it might or might not be an issue. When this would be an issue, so if you have a highest wait time of this SY scheduler yield, then that is where you'll have to start looking at, like, why we have a high wait time of the SY scheduler yield, right? So SY scheduler yield, whether the threads is not yielding, or whether the thread is currently executing for a longer duration, or why that is, why we have a highest SY scheduler yield. That is where you'll have to start looking at, right? So that is where all the queries are coming through the runnable queue and start executing on the CPU, right? That is the same thing, right? A runnable queue, thread pool, whatever it is that we have here. Okay, so running a current thread is currently different thread states that we have. So one is running, the thread is currently executing. Suspended, the thread is currently waiting for some resources, right? So it is waiting for some resources. I'll show you. So runnable, the thread is currently on the runnable queue and waiting to execute on the processor. That's what we were talking. So the ready to execute on the CPU. So as soon as the CPU is available, this thread will go ahead and execute on the CPU. So these are the queues that we were talking, right? Scheduling infrastructure, runnable queue, a list of processes that are ready to run, right? So the list of threads that is ready to run. So waited list, a list of processes that are waiting for some resource to become available. So that is what waited list. Worker queue. So you have certain workers, right? So there will be a workers and a new task is created. The new task will be assigned to a thread or worker, right? So that is what it is. The list of processes that are queued to given a scheduler are waiting to be serviced by active available threads, active worker threads, right? So if the thread is available, the task will be assigned to the thread and will start executing. Timer list, that's we discussed, like lock monitor is queued to the timer list. Voluntary scheduler yield of fixed time, whatever. Do not wait for resource like normal waits. This is the timer, right? So checkpoint, lazy writer, or lock monitor. So these are all is it in the timer list, right? So IO request, a list of in progress and pending IO request that needs to be completed, right? So we were talking if there is a, if it is posted some IO operation to be completed. That IO operation, the thread cannot wait for the so IO to be completed if it is asynchronous. The same thing, if the thread is posted IO, the thread cannot keep executing on the CPU. It should come out of CPU. That will be placed in the IO list that we have. Right. So this is the waiter list, right? So these are all like, so the same thing is a unordered list of threads that are suspended, right? So any thread can be notified at any order. No time limit for a thread on the waiter list, although execution timeout or lock timeout may take effect, right? So whatever time, there is no wait time or wait time that is not defined for this wait to be completed. No limit on the number of threads on the waiter list. There is no limit. So you can use this sys.dm underscore voice waiting task to show which threads are currently waiting and what they are waiting for, right? So you can use this DMV, select start from sys.dm underscore voice underscore waiting task. It will tell that what it is waiting for, what is the session which is running, and what is the duration it is waiting for, and you will have that information here in the sys.dm underscore voice waiting task, right? So we have this as well, like current waiting task, right? Suppose if you want to see this gives the information of your waiting execution. So we will talk these in the wait types that we have, right? So these are all gives that info, right? So runnable queue, again, like first in, first out, I was talking, it should be in the runnable queue, and whatever threads which are spawning, so all threads should be from the runnable queue, right? So that is what it is. Sys.dm underscore voice scheduler, where we can see the threads which are in the runnable queue. Okay.
Hello, will you provide that queries? What?
Sorry, what is that?
Will you provide that queries which are you are running?
I will. I have a Git repo, so I will share that Git repo to you guys, like so that you can access those queries. I will provide. Right. So let's say we were talking, just take some action and we'll see that, right? So let's say there are different, list that we have, right? Now let's assume that a thread which is currently in the runnable queue running, right? The thread is currently running. This is the thread which is currently running on the CPU, and we have different lists, right? So it is an I timer list, IO list, and this is a waiter list, and we have a available worker here, right, in the worker pool. Now, let's check the thread which is currently running on the CPU has to come out of CPU, because this will be either it meta yield pointer completed execution, whatever it is, right? So this is the runnable queue. I told you every thread which is executing on the CPU will be from the runnable queue itself, right? If I take this example, so it will be coming out of CPU and it will be placed at the end of the runnable queue because it needs to execute again. And it is placed out of the end of the runnable queue. And what is the first thread which is in the runnable queue is going and executing on the CPU, right? So it go and execute on the CPU. Next one, let's say IO completed. So whatever thread which is waiting for IO has completed, right? So IO, it was posted some IO operation, let's say backup IO, and it has completed. The backup IO has completed. As soon as the backup IO has so completed, then it will go and keep it in the runnable queue. At the end of the runnable queue, the thread will be placed in the end of the runnable queue, so that the next thread will be start executing here. Now, the thread which is in the timer list, right? So timer list, let's say there is a checkpoint thread, or there is some other threads that needs to be executed. It will be going at the end of the runnable queue again, so that it will start executing from here one by one. At the same time, like a waiter list as well, like whatever thread which is in the waiter list, then once the resource is acquired, then it will go and execute on the, as soon as it wait is completed, it will be placed at the runnable queue and the end of the runnable queue, right? So that is what it is. And if a task is created and if worker is available, then the worker will be assigned to the task and will execute. That is what here we will do. Yeah. So these are the states, thread states, right? So let's say, for example, a thread is currently pending. So it is, so let's say, for example, the task that you created, it is currently pending. So pending as in like the thread is not available to assign that particular task, right? If the thread is not available, it is marked as pending and will wait for thread to be available thread to be available to assign that thread to the execution. So at the same time, runnable queue. If the thread is in the runnable queue, then the thread will, if the thread is in the runnable queue, then thread is marked as thread is waiting for CPU to be available. Some other thread is currently running and waiting for signal from the thread which is currently executing on the CPU, right? I have a thread and no CPU. So here the running. So if the thread is currently running, I have a thread and I have a CPU and currently executing on the CPU, right? So if you see the status as suspended, then it is waiting for some resources. Let's say, for example, blocking. So if you have a blocking, then the status will be suspended. So if it is a sleeping, it is not doing anything. It is just left it open and not close the connection. So that is how, that is the states that we see even if you execute sys.sys processes, so catalog table. And this is how the handling and worker request decision, right? So let's say you have an incoming request and it will check whether an idle worker is available or not. If idle worker is available, send the request to the worker and then it will proceed with execution. So if the worker is not available, right? So it will the worker limit has reached. It checks whether worker limit has reached or not. If worker limit has not reached, then the worker will be created and assign the worker to a specific task or request, right? Or if the worker limit has reached, then work will be in the queue. The task will be in the queue until a thread is available to take this task, right? Assign this task, right? This is the flow of, so the thread assignment and the execution, right? So whatever the incoming task which is coming in, it will be executed by a thread, right? So this is how the thread scheduling works, right? So right, so I'll stop here. So any questions with respect to the scheduling threads, or is it too much, or anything that you understood? So whatever queries that we have, so I'll show you that.
Yeah, it's a lot of it's a lot of information to digest at this time, but I want to ask a question I usually see at work. Like when you look at the monitoring tool, sometimes you notice that you're getting SQL timeout. Now, when you look at it, you see that you're seeing like using CPU, not waiting. So in situations like that, what do you do?
You mean that high CPU weightage?
No, you will see like when you go into the monitoring tool, I'm giving the specifics with App Dynamics. So when you're using App Dynamics and you see SQL timeout error, it gives you some more information on where you're coming from and where you're going. So when you go to the wait stat, you will see sometimes you see things like using CPU, not waiting in App Dynamics, something like that. So how do you troubleshoot that with related to what you've taught?
So I don't know what is the wait time, right? So let's say, for example, the queries are waiting for some resources, like either it is whatever issue. So this is the, so the internal things that it is waiting, right? For example, let's say the query is waiting for some resources. So if waiting for some resources, then definitely we'll have to understand what is the wait type, and we'll have to start troubleshooting on that. So whatever I have explained here so far, to understand how the threads and scheduling works or their behavior, right? So that is what I explained, right? But if the query is waiting and you see that high CPU utilization or high IO operation, or any wait type that we see, so we will be discussing that in the coming session, right? So the query is waiting for some resources. So how you will start looking at, where you will have to start looking at, so that we will talk. So whatever I have discussed, so this is the actual behavior of the thread scheduling and thread utilization and all, right? So for example, let's say you have exhausted number of threads. So if the threads are exhausted and you don't have enough threads to available, so that is where, like, so we were talking uh the high threads and high number of threads, and where we can see like we have the TMVs and all, like we were checking. But to answer your question specifically, so we will talk in detail, like, so what is the wait types that we have and how to troubleshoot wait types.
No, it's not on the wait types. I'm talking about you. I don't know. Probably I will take a shot of it and make you see it. You'll see that what you're going to see that it's using CPU, not waiting. So I want to understand if it's related to, if it's running or
Yeah,
related to the
if it is not
traits.
waiting, then this is running one. That is what, right? Like here I have shown. I don't know whether I'm able to understand your question or not. But if I see here, so if the thread is not waiting for any resources, then you will see the status as running. So if the thread is currently running, then the thread is currently running on the CPU and not waiting for any resources.
I'm gonna no, don't worry, I'll probably get a screenshot, then I'll send it across to you in the next class so you can understand what I'm saying.
Definitely, yeah, that works.
So in the case of the suspended mode, the suspended one, what are you supposed to do? Like, it's waiting for IO to be available, so you just let it wait, or is it something that you then troubleshoot further, or what?
No, we cannot troubleshoot. Let me show you this. 1 second. Suspended you are talking, right? So for example, let's say you have this begin tran. Just take an example. Begin tran. Select let's say query. I'm just enabling that implicit transaction. So I'm just executing select start from what's this? So I'm just executing, and if I take this begin tran update person, right? I'm just okay, fine. So let me do the Let's see. Okay. So how to check like what is the status of the sessions, right? Select start from, we have different DMVs for say sys dot sys processes, for example. And if I take that specific session ID or speed equal to 69, for example. If you see that 69 is currently suspended. So 69 is currently suspended. So it is waiting for some resources. If you see that suspended, it is definitely waiting for some resources. What it is waiting for, that is what we have the wait type. So or the blocking, like if it is waiting for any resources, it will be in the suspended state. Then we'll have to understand what it is waiting for. If it is a blocking, then again, like, so we'll have to check like, so what is the blocking, what is the head blocker, what is how to proceed that head blocking query and all, and maybe we'll have to ask the application team to close the connection. So let's say it is waiting for some resources. Let's say, for example, SOS scheduler yield, right? So if it is SOS scheduler yield for longer duration, then it will be in the suspended state. So no, sorry, my bad. Like SOS scheduler yield, you normally see if it is a runnable state. Runnable state equal to runnable. So if you see that suspended, it is definitely waiting for some resources. Let's say, for example, page IO latch, page latch. And if it is waiting for any such resources, then it will be status is showing a suspended. So definitely we will have to troubleshoot why that is waiting for so long to get it done, right? If it is locking, then we'll have to ask application to close the connection. If it is waiting for some page IO latch, for example. So we'll talk about the latches and all, but if it is waiting for page IO latch, the page is not available in the memory and there is an IO operation to be performed, right? So it could be a memory issue, or it could be this storage issue, or it could be anything, right? If you have a highest page IO latch wait types that we have, or latch, or memory. So whatever it is waiting for, so you will see that status as suspended. So if it is suspended, definitely you will have to look why it is suspended and what is the resource it is waiting for. Otherwise, the query might take longer to execute if you don't take any action. So you will have to, if you notice any suspended sessions, you'll have to understand what it is doing, whether it is a blocked or it is waiting for some resources. Then we will have to start looking into that. So I'll show you the we'll talk like detail like during wait types. But here that definitely you'll have to start looking at. Okay, did I answer your question?
Yes, yes. I just wanted to know, like if it's suspended, we didn't have to look at what wait type, and then from there onward kind of figure out what's happening, why that wait is happening.
So you'll have to look into that, like why waits are happening because of the wait type that we have. So what wait type, and it all depends on what is the wait type. For example, let's say you are reading huge pages, right? So then it will be a page IO latch or page latch, whatever it is, and again it will go to the query performance, right? Why we are reading huge pages, so from the table, entire table. So again, it will go to the query performance, and we will have to, so look at the query performance as well by collecting execution plans and indexes, statistics, or fragmentation, or there are many things that we will have to. So that's why, like, I haven't mentioned here, but we will discuss detail, like, so if it is suspended or if it is waiting for some resources, what we will do.
Right.
Not every weights, maybe a few weights I can show you and I can explain, but there are n number of weights, right? Suppose if you go here, sys dot dm underscore voice underscore weight stats, so you will have that. If you aggregate, so group by the relevant, you will have that many, like around 872 weights with respect to different, so weight categories that we have, right? So we cannot touch base everything, but a majority around 10-15 weight types that we will talk, so understand like how to reduce the weight types and how to go forward. So we will talk that details.
Okay, thank you.
Sure.
So I have a question. Will you be able to clarify how to monitor thread exhaustion? Say, for example, you have a server with 4 CPU, and you know that with 4 CPU, maximum that SQL Server could create is 512 thread. So in this scenario, right, what parameters or which DMV could you use to monitor when you are hitting this maximum number of 512 thread? So in my scenario, I try to use PEFMON, performance monitor. On that process, there is a metric called thread. So, but when I check it, the value I'm seeing is way higher than 512. Now in OS scheduler DMV, you have columns like active worker count and current worker count, right? So there are all this information, but I'm not sure exactly which one to use to monitor when your thread count is getting high. Will you be able to explain this?
Yes. That is very valid question, right? So 1 second, let me see if I have any query. I'm just checking that. If not, what you can see, let me see here. So there are different methods that you can see, right? sys.dm underscore OS. That's this. Okay. So you can validate that perfmon, but the perfmon, so you'll have that thread count in the perfmon as well. But in the DMV that you can see, okay, 1 second.
So in OS scheduler DMV, you could see
Correct. So
current
OS
worker
scheduler,
count.
correct. So let me see. Let me write that. Select star from sys.dm underscore OS underscore schedulers where status equal to
Online, visible.
Online. So if you get that, you'll have that visible online. So in this DMV, so what you can see, select CPU underscore count from sys.dm underscore OS underscore sys info, right? So you can get that CPU count, like whatever it is. So CPU count, right? So from here you can get the CPU count. From here, then select max worker count from sys.dm underscore OS sysinfo as max worker, that you can find the max worker count from the select star max worker count, right? So you can get it from the max worker count. Sum of what we call, so active worker count, active worker count, so you can consider that current threads.
The worker with an S.
What is that?
Workers.
So okay, so correct. So active workers count. That you will get the current total active worker threads, right? So you can calculate select max workers count. So, or you can just use this, right? So for example, if I take this current worker count, right? So max worker and current threads, right? So you can just this you can calculate, right? Based on this, if you just subtract these two, and you will have the total available workers, whatever it is. So this way you can monitor the current workers which are created, or even perform, like, so you can just check that what is the workers which are created and all. So second thing, right? So the which I also follow, right? This is one thing that we'll definitely have to look into. Second one, right? So if you go here, extended events system, starting from 2012, like that we have, so something called, I'll just clear up this, clear, apply, okay. Right, so system, if I go here, the query processing, filter with the query processing, right? So in the query processing, so currently it is 9th, and if I just filter out, let's say for example, this is what we have. So you can see here workers created and workers idle, right? So you will have that information here as well. This is sometimes I'll definitely look if there is, let's say for example, thread exhaustion happen and you want to investigate the issue. So in that case, you want to identify the root cause, and you cannot execute this to get the root cause, right? So this is just a current worker availability and current worker created. So you can find that information from the extended events, system events, event file. There are two files. Like you can go to the event file, double click or right click and view target data, and you will have this, and you can just filter with the query, filter the component with the server diagnostics, and you can just right click and show that. For example, if I just remove that and show column table, so you'll have that, and you can filter that query processing, where you can see that information here, workers created, how many workers created, and what is the time that the workers created, right? So you can have that the historical information as well based on number of files which is created, right? So you can find this information from the extended event session as well.
Okay, so the one in Perfmon is not accurate.
Performance, you will have the current data, so that is accurate. So performance monitor, suppose if you have that historical data captured in the performance, that is valid. But let's say for example, you don't have any performance captured continuously, or so you don't have uh, any tables which are created to load the thread value and thread creation and all. Maybe this is where you can validate this as well. The extended events will give the same info. So even performance, if you're polling that continuously and loading the data somewhere, or you have third-party tools or anything which is capturing the performance data, that is also valid. But if you don't have anything captured, and if you run a performance monitor after the issue happened, you would not see the behavior. So it will be a different thing altogether, and you'll have to work on. You'll have to look at, so one way is to validate the system extended events to see what is the thread creation.
So in this extended event, how did you get the column, the data column? Right.
The same, right click and hide, and right click and show the column.
Okay.
Right, you can see that state, right click and show column and table. Suppose if you see anywhere which is a warning other than clean, so that is where you'll have to start looking at why it is going warning and all, like whether either threats are exhausted or anything else that I'll have to look into. There are many things which is useful. Maybe while talking extend events, I can show you a high level. Like suppose if you have non-preemptive high weights types and all, and we can talk that. But just for your information here, we can monitor thread creation and thread utilization based on the extended event as well.
So when you open the extended event, you filter by what?
So first thing, SP
Sorry.
underscore server diagnostics. No problem. So first thing, SP underscore server diagnostics, where we'll have to look, for example, filter, clear, filter, apply, okay, right? So everything you'll have. So SP underscore server diagnostics, what you will have to start looking at. And the component, if you see that, we have something called query processing. So you'll have to scroll down and you have something called query processing. So if you execute, I'll just show you server. If you execute this stored procedure, so it executes and gives that 5 so resources, right? So 5 components. So we can call it as a system, resource, query, processing, and IO subsystem and event, right? So the description, the data that we have it this way. So workers created, workers idle, whatever it is, and query processing. So this query processing, so query processing will have to filter with, right? Right click and find filter by this value and filter query processing, apply, okay. Right, so this is the one that you'll have to filter with query processing.
Okay.
So yeah, we will talk about the extended events later, right? So any questions on this today's session? Okay, cool. So I think it is late for you guys. Like we will disconnect for today. And if you have any questions, we can talk. Maybe tomorrow we'll connect and we'll discuss more. Okay. Cool. Thank you.
Thank you very much. Thank you.
Thank you. Bye-bye.
Thank you.